Okay. Let me. I guess actually I should do present first. Okay. So hopefully you can see my screen now, right?
Yes.
Okay. So today I'll be presenting on Kalman and particle filters. This is going to be a little math-heavy presentation again, but hopefully you understand how a Kalman and a particle filter works and how to tune them and what parameters we actually will adjust to improve the filters. So, okay. So yeah, again, just I'm Andrew Yaraboy, fourth year mechanical major, CS and intelligence minor. I'm in the RoboNav software team, and this is me doing model rocketry and also making a door lock for my dorm freshman year that used a fingerprint scanner. I don't know, just random stuff.
That's a good idea.
Yeah, it worked. It was pretty good actually until the last week where we had to take off the lock, and both my roommate and I completely forgot that we should bring keys like 4 times in a row because we were so used to not bringing our key to our dorm. So it was a good idea, but yeah, it has its drawbacks. Anyways, so some terms for that we'll be talking about today. So state estimation, and it's basically what it sounds like, estimating the state. And usually this is the pose of the robot, but it can also include like velocity. It can include a lot of other things. So estimating the state of the robot or landmarks. State estimation, if it's estimating the robot pose specifically, and that's called localization. And typically localization refers to when you already have a map and you are just trying to find out where the robot is in the map. Mapping is the opposite of that. So it's generating a representation of the world. So we know where the robot is, but we want to use that to build a map. And then SLAM is a combination of the two. And so it's simultaneous localization and mapping. So you're trying to map the world, but at the same time, you're trying to figure out where you are in that map. Navigation is just planning a path to arrive at a desired pose, while motion planning is planning a sequence of steps to carry out a task. So those two they sound kind of similar, but they're actually different. Typically, navigation is like used with actually like moving platforms, while motion planning is often used with like robotic arms. And I mean, it can still be used with moving platforms. It's just like more specific, I guess. Sensor noise. So we talked about sensors a while back now, but sensors aren't perfect, and in reality, you get a lot of unwanted variations in the data that do not reflect the actual quantity we wish to measure. So, for example, in this chart, you can see there's a lot of noise, and that green line, that flat green line, is what the actual state is. But the sensor is doing like giving you readings all over the place, and we oftentimes use filtering techniques such as a Kalman filter to try to limit this noise and reduce so that we get a much like cleaner and closer reading to the actual to the actual state of that we want that we're measuring. That sensor noise. An important concept that you'll see in both models is a sensor model. And this is a mathematical model that describes the relationship between the sensor output and the actual value of the measured quantity. So for example, if we have a sensor and say this is like a LiDAR sensor, and it's sending out a beam and it's measuring the distance to a wall. So in reality, the sensor is likely to give you actually like a graph, something like this. So it's not necessarily going to give you the actual value you're looking for. Most likely, there's going to be a small chance that it's going to give you some like random value, and then there's going to be a much higher chance that it gives you the correct, like around the correct value. And then oftentimes you'll, in a lot of sensors that are like distance-based, you'll see these peaks at the very end. And this is because if the sensor doesn't, like say it emits a pulse and it doesn't receive it back, it'll essentially set that distance as a max, like to a max distance. And that can be, well, so like essentially all the noise that's accumulated past this point will essentially be all bunched up at this max distance. And so this is kind of a typical sensor model. However, we'll see later that although this is like what an actual sensor might look like, we typically will just use this center portion here where it's like a peak to represent the sensor model, and we'll kind of ignore these effects at the ends. So yeah, so speaking of what we will use as a sensor model, one very common one is a Gaussian function. So they're also called normal distributions. And this is the formula for a normal distribution, but it essentially just has two parameters. It has a mean and a standard deviation. So everything else, as you can see, is a constant, essentially. Gaussian functions look like this. And essentially, as the standard deviation increases, you will see that the Gaussian function becomes more flat. And as it decreases, you'll see it becomes much more peakier, as like here. The mean essentially tells you where the center point of this curve will be. So the mean here is 0 for the blue curve, and has a very low standard deviation. The red one has a mean of 0, but a very high standard deviation, or relatively high standard deviation. And then you can see that this one has a mean of -2, and it just gets shifted over. So a really nice property of Gaussian functions is that they have a total area under the curve is equal to 1. And so they're very useful for representing probabilities. Because essentially for anything to be a probability has to, the sum of all states essentially has to be equal to 1. So that's why we use Gaussian functions. They're also very, if you have a random event that occurs multiple times and you sum it up, it ends up being kind of Gaussian. So there's actually like truth behind this model of like why a sensor would give you a Gaussian distribution. So I mentioned standard deviation, but in case you've never heard of it, or if you just need a refresher, the standard deviation is a measure of how spread out the values are, and that's why we saw greater standard deviation resulted in a wider curve. The standard deviation squared is called variance. So it determines the width of the normal distribution, and less noise means smaller standard deviation. So how it's actually calculated is basically with this formula, where it's the square root of the sum of differences between the actual measurements and the mean of the measurements, and that gets squared and divided by n. So if you had, say, 4 measurements here, and it's 10, 5, 12, and 13, and you calculate the mean of this, and you will get 10. And then you do this calculation, so you can just sum up all those differences, and you get a standard deviation of 3.08 in this case. So, yeah. So variance is, as I said, it's just standard deviation squared. And typically we will work with variance, and that's just kind of a convention. There's also because of covariance, but so one thing to notice is that if you multiply a vector z, like the one previously, and you multiply it by 2, the variance will actually increase by 4, and that's because it's 2 squared, and that's just because both z and the mean will increase by 2, so the difference will increase by 2, and then it gets squared in this formula. So And we'll come back to that later. You'll see that in the Kalman filter that this happens as well. So the other thing that we need to note is covariance. And essentially, it's very similar, but it relates to variables instead of just one. And the variance is basically the covariance with of the variable with itself. But as you can see, this is the formula, and the covariance is positive if greater values of x typically correspond with greater values of y. And covariance is negative if the two variables are inversely proportional. So greater values of x will result in smaller values of y. Yeah, that's basically that. And with that, we have everything we need to start talking about the Kalman filter. So actually, any questions on the previous material before I move on?
Would it be bad to say like covariance is just like a matrix of derivatives?
So a matrix of derivatives. It's not exactly a matrix of derivatives. Yeah, that wouldn't be quite accurate to say that covariance is a matrix of derivatives, but it is. It's more about the spread and how the spread, like how how the data is distributed. It's not so much the derivative or anything because yeah, it's not time. It's not with like respect to time or anything like that. So yeah. The covariance is, so it's also, I should note actually, you bring up a good point that covariance, it can also be represented as a matrix. And the covariance matrix is basically a matrix with the variance along the diagonal and the covariance of each like variable on all the other positions. And I think I'll have a slide that shows it, but yeah, we typically use covariance as a matrix, actually, in that matrix form. But first, I guess, let's continue with the Kalman filter. Kalman filter is an algorithm that lets you combine multiple sensor readings to get a state estimate. And it is very commonly used for localization. I think it's the most common localization technique anyone uses. It's also used a lot for just using sensor data and for like, yeah, for controlling things, essentially, to get your position and to get better readings. So so we will look at a 1D robot here. And the formulas I'll present will essentially, they can all expand to 2D robots and, well, to any dimensional space, really. But we will just be talking about 1D just because it's a lot easier to visualize. The robot that we're going to be looking at has one noisy sensor that gives us a distance to a wall located at x equals 0. So if here the robot is probably at 10, and z here represents the sensor reading. So the sensor says we are 10 meters away from this wall, but yeah, and that probably means that x is around 10. But as we'll see, it could be 10.1, could be anything. The Kalman filter has two steps. There's a motion update. And during the motion update, you actually lose information. And what that means is you'll see that that variance will actually increase as you take a step. And that makes sense because like if you have a robot and it moved 10 feet forward, it might have moved 9 feet forward, it might have moved 10, it might have moved 11. And so there's some uncertainty about how much it actually moved. And so you're losing information about where you are whenever you move. Then there's also going to be a measurement update. And this essentially is where we're going to fuse the data from our sensors into our model. And this will actually give us information. And again, this makes sense. If a sensor says you're at 10 feet, you're probably at 10 feet away. Yeah. So yeah, and this cycle will basically repeat many times a second. You'll have a small motion update where you move a little bit, and then you'll have a sensor reading come in, and you'll update your estimate, and then you now have a new position, and you're going to just repeat this over and over. So there's going to be a lot of matrix multiplication in this, but you can also think of these as just numbers for 1D case, which is why I kind of take a look at it here. And so essentially, this is the first formula of the Kalman filter. So here what we're doing is essentially we are finding the predicted state based on our previous state, how we think the model moves, and any control signals we're putting in. So yeah, and as you can see, they're basically multiplied, and A and B, which A is the state transition matrix, which just tells us how we advance over time, and B is a control input matrix. These two matrices essentially define how our model works. Usually these are pretty constant, although you'll see that delta t, which is like time step, often shows up in both of these. Going into example of what this would look like. So say our robot is at position 5 or 5 meters, and it moves over to 7.5 meters. So our previous position was 5, and that's just x k minus 1. Then we have some input velocity, and this would be like us telling the motors to go at a certain velocity. So say that velocity would give us 5 meters per second. As you know, like the position plus velocity times the change in time is going to be equal to the new position. So we're doing the exact same thing here, but we're expressing it as in this form, essentially. So A is just going to be 1 because the previous position, we're just going to assume that it stays the same, but it plus whatever velocity we inputted times the time step. So sorry, B here is actually just the time step. And so we just have essentially 1 times the position plus the time step times the velocity. So this is exactly the same. It's just we express it in this form because when we go into a more complex examples, such as when your state is at 2 values, then it's much easier to express it in matrix form. Here we have essentially the previous position is going to be equal to the position plus velocity times time plus acceleration times the step in time squared over 2. And then the velocity is going to be the velocity plus the acceleration over 2. And so now our control input is acceleration. And that's actually quite common because, if you're using torque control, you'll be inputting accelerations essentially. And then you have the time step, and your state is now 2 numbers. It's actually a position and a velocity. So our robot here is at position 5 and moving 2 meters per second originally at time 0. And then at time 1, we are trying to figure out where will it be and what will its velocity be. So our A now becomes a 2x2 matrix, and Kalman filters are into they use matrices a lot, so you can't get away without understanding that they are matrices and using matrices. So here we're basically converting these 2 equations into a matrix A and B. And if you apply this formula, you'll see that we're essentially doing the exact same thing we do here to get our new position and velocity. We're just doing it with matrix multiplication. As we move, though, like I said earlier, we're also losing information, right? So what's happening is this curve is getting flatter. So we moved from 5 to 6.125, but we're now less certain about where we are. And we need a way of representing this so that our model understands that we are less certain and can take this into account. And so the second part of the motion model is to essentially calculate a new covariance matrix of that estimate that we previously calculated. And this is, it's actually quite intuitive what's going on here, but it's just the matrix makes it look like matrix multiplication makes it look a little complicated. But basically, there's the current state covariance matrix, which is a matrix full of the variances along the diagonal, and then the covariance on all the other places is essentially equal to the previous covariance matrix times, well, A and then A transpose. And this is actually just basically A squared. You can think of it as A squared. And this is like, if you remember, we found out that 2 times the, if you multiply a vector by 2, its covariance actually its variance increases by 2 squared. And this is the same thing. We're basically multiplying that vector by A earlier. So its covariance is now going to increase by A squared. But with matrices, you can't just multiply, you can't square a matrix exactly because it actually gives you something else. And so to do the same thing, we have to multiply it by the A and then the A transpose. And then you'll see this extra term here, which is process noise. And this term is actually really important. This is one of the terms you're going to usually tune in a Kalman filter. Because A is actually kind of defined by your system. Like, you don't exactly tune it. It's just whatever your system is, it'll have a particular A matrix. But or a state transition model. But the Q is something you tune to try to improve your filter. So yeah, breaking it down further, here's the actual covariance matrix. I should have set that on the slide. Yeah, so you can see it's basically variance along the diagonal and then covariance here. You'll also notice it's symmetric, and that just means that if you transpose it, it's the same matrix. Yeah, so this is our state vector. If we are in 1D, this simplifies to just the variance, which is sigma squared, and sigma here is standard deviation. So yeah, yep, and then. Yeah, so this first term is basically, like I said, it's just the same thing we were doing earlier. We multiplied the state by A, so we have to multiply the covariance matrix by A squared. And if we look at it in 1D, for example, APA, you basically get A variance of X times A transpose, and A transpose for 1D is the same thing as A. So that becomes this, and then you see that it's A squared times variance. And then there's Q, and Q is, like I said, is important, and it's the process noise. So this represents the noise that naturally occurs as you move, and this is the loss of information every time step, essentially. So in our 1D example, this variable captures the fact that if we move 1 meter forward, we are less certain about our new position, but like in any dimension, if you change state, you're less certain about your current state. And then Q changes with application, and it can be kind of difficult to calculate in practice. So a lot of it's based on intuition. Well,
oh, sorry.
Yeah, that's a long message, but do you want to say what you were?
No, I wrote it before you said what you were saying right now, so you're good.
Oh, okay. Okay, yeah, so Q changes with application, and it's difficult to calculate in practice, so you can choose it by just based on intuition, but you can also calculate it by having your robot like repeatedly move forward, for example, and then measuring exactly where it is, and trying to use that to figure out, well, measuring, the way you measure it has to be more precise than your sensor. So you would have to like use a tape measure, for example, and measure exactly where it is. And then if you repeat that many times, you can plot it, and then you can essentially figure out Q that way. But a lot of times it's like chosen just based on intuition. And what increasing Q means is that we trust our predicted state less. So it means that we think that when we're less certain about where the robot will be after it moves. So a really large Q means that, like, say our motors are terrible, we would give it a very large Q so that because we don't really know where the robot is, and that's just telling the model that we don't know. Yeah.
So just one more note that I did actually want to point out. The reason that you can't, so in theory, the actual calculation of Q on a system that is perfectly like we think it is, like the things that we've assumed so far, it's actually really easy to calculate, right? You would just basically, I mean, if you have a good estimate, right, you can just sum up, or you can just use like sensor measurements, right? If you have a good ground truth sensor reading, you can just use that. But in practice, you can't do that because real world robots are not these magical linear systems. So we made the assumption here that like all the noise that we're adding to the system, right? Any disturbances that you get, right, that move your robot around are Gaussian, just the same as our sensor model, right? In the real world, that never happens. You're going to get a lot of noise when your robot is moving really fast or when you're, applying controls to it, but you don't expect your robot to just vibrate around when it's sitting there on the table. That would be really disturbing.
Yeah.
That's the model that we're assuming here, right? We're assuming that noise is exactly the same whether we're moving, at 10 meters per second or just sitting there, which is sort of why this breaks down, or why you have to do this intuitively and pick sort of a guess rather than having the exact value.
Yeah, another thing is, say your robot's moving on different terrain, like your Q value will realistically change as well. Like it based on exactly like what the surface is you're moving on, it'll change. So it is kind of based on intuition, and you're trying to get this variable into like the right ballpark essentially. Yeah. So in summary, we have these two steps for the motion update. The first step, we are predicting our new state. And the second step, we are determining the covariance of our new predicted state. And this lines up with basically just two Gaussian curves, where the new state is just this peak. And as we saw, it moved from 5 to 6.25. And the covariance increased because of this Q value. And it basically widened this out so that we have a much less certain guess of where we are. So that's all for the motion update. So now we'll talk about the measurement update, and hopefully we can gain information so we actually don't end up just being completely lost. So like if you didn't have a measurement update, and you just kept moving, eventually you would have no idea where you are, even if you had like a perfect initial guess, because that covariance would just increase forever. So a measurement update, and this is probably the most scary slide, I would say, in this whole presentation, is this Kalman gain equation here. So there's a lot going on, but you actually, to derive this, it's not too bad, but there's a lot we would have to talk about. So instead, I'm just going to give you, I'm trying to give you an intuitive sense of what the Kalman gain does. And also, we'll show two examples so you can see how it actually it ends up working. But the Kalman gain represents how much we trust the motion update compared to the sensor update. So a large K actually means that we trust the sensor more. So yeah, you can see this is just the formula for it. And there's a new matrix here called H. And what H is essentially, it's a way of converting your state into a predicted sensor reading. Yeah, it maps the state vector to the sensor measurements. So your Z predicted will be equal to H times your current state. If a lot of times this is just 1, so say your sensor gives you your position, and your X, the thing you're measuring in your state, is just your position, then H would just be 1, because essentially if you're at 5 meters, you expect your sensor to give you a reading of 5 meters. Yeah, so a lot of this can be 1 here, and then basically simplifies down greatly, but sometimes it's not 1, and therefore we have a matrix for it. Yeah. So R is also a part of this Kalman gain, and R represents the measured noise of the sensor. So in the 1D case, this is just the variance of our sensor. And there's two real ways you get R in real life. One is you do a bunch of tests, and this is actually pretty easy. What you can do is, for a GPS, for example, you could place it on a table and have it stationary, and then you just get a bunch of readings, and you just look at the standard deviation of those readings, and that could be enough to basically compute R. Another thing you can do is look at a data sheet. So a lot of sensors will give you variance or standard deviation or uncertainty, and all of these can be converted into the variance you need to essentially calculate R. Another thing is R, oftentimes what we'll do is we only calculate the variance, and then we kind of ignore the covariance portions. And so you get like a diagonal matrix for this. So R looks a lot like P, essentially, but just for your sensor. And so to try to give you an intuitive sense of like what's going on here, we're going to look at two cases that are like basically the complete extremes of. So one is you have a perfect sensor, and this sensor has zero noise, so it gives you the exact position you're at. So in this case, R would equal 0. And so we just plug it into this Kalman gain formula. And what you'll see is that essentially we'll take the inverse. And when you take the inverse, you actually flip the order. That's just like a small detail, but this is just calculating it out. And what you'll find is the Kalman gain will just be your H matrix inverted. So now if you plug it into the second step, which is where we're calculating our actual position, essentially, based off of our predicted position and our sensor model, what happens is that H inverse gets plugged in, you distribute it, and if this thing goes away, yeah, you distribute it, and what you'll find is that X will equal the H inverse times Z, K, and ZK is just your sensor reading. So what this actually means is that your position, your final estimated position, will just be whatever your sensor tells you the position is. Essentially, our predicted the predicted state we did, all the calculations we did earlier, they don't factor in at all. And this makes sense because if you have a perfect sensor, it's giving you your exact position. You don't want to be estimating your position based off of like your motion model. You just want to use the sensor. However, say you had a garbage sensor, and this sensor essentially is just noise. Like it doesn't actually give you anything. Then it's uncertainty, or I guess, well, yeah, its standard deviation would be infinite because it would be just like a flat line. Sorry, wait, if the sensor doesn't give us all the state variables in the perfect sensor case, what if the sensor doesn't give you all the state variables? So yeah, that can happen. And in that case, you can set it to 0 essentially, and yeah, you just set it to 0 because it's adding. It won't affect it essentially for those measurements. And what we'll talk about later also is that you can actually have multiple of these. You can repeat this step multiple times for each sensor, so that way you can actually fuse the data. But I'll discuss that a little bit later. Yeah, so say you had a really bad sensor and it's giving you basically no information. In that case, you'd be adding essentially like an infinite value to some value, so you don't really care what this is, and you just get infinity, which inverted is basically 0. So your Kalman gain is going to be 0. And then that gets multiplied by your sensor reading minus your predicted sensor reading, essentially, and that goes to 0. And so what you end up doing is you're just using the estimate that we used from our motion update. And again, this makes sense because if the sensor is not giving you actual information, then we should just use what we predicted our position to be. And that's exactly what the Kalman filter will do. Given you choose R correctly, because R is a parameter you're setting. So if you know your sensor is garbage, then you shouldn't be using it. But like technically, if you set it, it wouldn't hurt. If you set it to infinity, it wouldn't hurt. And so the last step will also be updating the covariance matrix. based on the Kalman gain. So so here we have this is a little hard to visualize, but looking at the two cases again, if you had a perfect sensor, then K would be H inverted, and H inverted times H is the identity matrix. Identity matrix minus the identity matrix is 0, so it's a 0 matrix. And then essentially your covariance is 0. And what that says is that if you have a perfect sensor, you know exactly where you are, and the covariance of your positions, so like how certain you are about where you are, you're 100% certain because there's no uncertainty at all. So for a garbage sensor, though, what you'll see is that your previous estimate, like the covariance matrix that you got before, it's going to stay exactly the same. It's not going to get changed at all because Kalman gain is going to be 0. And so the identity matrix times the covariance matrix is just the covariance matrix. Yeah. So together, this basically is the entire Kalman filter. So you have the prediction state step where you get a new prediction of where you are, and then you also update your covariance matrix to for the predicted state. And then you notice that these two are getting plugged into the second step of the correction step. And we're calculating a Kalman gain, which uses this just formula, essentially. And then we're looking at the current state is basically going to be the current state times the Kalman gain times the actual sensor reading minus what we predict the sensor reading to be. And yeah, and that's basically just gives you our current state, and that's where we're fusing the sensor data. And then lastly, we update the covariance based on how much we essentially use the sensor or how much we use the predicted the predicted state. So that's basically it. The one thing is here you if you had multiple sensors, one thing you would do is you would essentially run one prediction step for a certain amount of, like, usually this would be like, say, 10 hertz. So for every 0.1 seconds, you are running a prediction step. And then for all the sensors that you got during that step, you essentially do a correction step for each sensor. And you would do that repeatedly. And then at the very end, once you've done that for all the sensors, you would use this xk as your current state. So this is what we want, actually. It's just where we are, and then sometimes it might be like your velocity, it'll be your like angle and stuff like that. And then also the updated covariance is actually, it can be useful. Typically you kind of ignore this, and this is mostly just used for the next loop because in the next loop, xk becomes xk minus 1, and this just repeats over and over. So yeah. And visualizing kind of what it's doing. Unfortunately, this doesn't have like your initial state, but essentially your initial state would be, say, like somewhere here, and it would be taller than this red peak, probably about the same height as the green peak. And essentially you moved, so then you got your prediction estimate, which is this red peak, and then you got the measurement, and that comes with its own distribution. And what you're calculating is this Gaussian function, essentially, and then between the two. And notice that it's closer to the blue peak than the red peak because the blue peak is taller, essentially. It's because we're more certain about our measurement than we are about our predicted pose. So the green, the actual predicted state, ends up being closer to the measurement in this case. Also notice that it's more certain than either of the two peaks. And that's just happens, that's what occurs basically in here. Your covariance actually ends up being higher than from the predicted state or from the measurement alone. And that makes sense because you have more information to work with. And the more information you have, the more certain you'll be about your pose. So this is a couple of things to note. This first one actually got asked in an interview before. Like, what's the most expensive step in the Kalman filter? And it's getting that inverse. This actually matters because, as you'll see, there's a lot of different versions of it. And right here, when we calculate this inverse, this is the most expensive step of the Kalman filter computationally. And that's just because inverses are hard to calculate for computers, and it happens O of n3. There are optimizations. Sometimes they'll sparsify the matrix, which means they basically put in a bunch of zeros for all the small values, and then they can get that down to like O of n to the 1.5. But no matter what, it's still the most expensive step of the calculation. Another big thing is that it assumes a linear model. So if you noticed, those matrices we multiplied by, they can only be essentially that matrix times the state. Like it can't do the times the state squared. It can't do anything like that. And it also can't use trigonometric functions to apply to the state. So it's only linear, and that's a huge limitation because most robots aren't linear. I think almost no robots are linear. If you have a 2D robot, its angle is not going to be linear. So like, I guess it can be, but it's a big assumption we're making here. The Kalman filter also is unimodal, which means that it can only track one position at a time. So if you go back to here, you can see that it has an estimate. Essentially, what you're getting at the end is this green bell curve. But what if, say, the sensor readings, say you enter like a room and you know that your map has two identical rooms that look exactly the same. For a while, you wouldn't be able to figure out which room you are in because all the sensor measurements you're getting will be exactly the same for both rooms. And what the Kalman filter will do is actually quite unfortunate. It'll basically say that you're in between the two rooms because it'll have like, it'll maybe pick one, or it'll say you're in between the two rooms. And essentially, you're going to have a lot of issues with the Kalman filter working in a case where you have two like identical like scenes, I guess. Yeah. So big things. Also, let's see. Also, you can do it offline. Yeah. I'll also talk about a little bit some of the stuff with these affect our teams. How do you come? So yeah, they do affect our teams. Good question. So this linear model assumption, this doesn't work for, I think, at least for RoboNav, I know for a fact it doesn't work. And so we actually do get over it using these other versions of Kalman filter, which I'm about to talk about. Yeah, I'll talk to this and I'll say how we use it. But essentially, yeah, so there are three main types of like other Kalman versions, but they're all a Kalman filter with like some added stuff, essentially, and they are all they're all very common in practice. I think extended Kalman filter especially is like super common, but so the one filter you might hear about is information filter, and this is actually exactly the same as Kalman filter, except what they did was they inverted what you're keeping track of. Essentially, instead of keeping track of the new state and the covariance, you're keeping track of information and I forget what they call the state inverted, but there's like basically you're inverting everything. And what the benefit of that is that this inverse that's really expensive to compute now occurs in the prediction step instead of in the correction step. And if you have a bunch of sensor readings that are giving you, well, a bunch of like, say you have like 3 IMUs and they're all giving you essentially the same information. What you can do is, instead of doing this correction step 3 times and taking the inverse each time, you do the correction step 3 times, but you don't have to take the inverse because it only happens in the prediction step. The reason I don't talk about it is because, first of all, it's not actually as common as the Kalman filter, and second of all, it's harder to it's harder to understand because it's not as intuitive as just your state and your covariance matrix. It's a little more complicated to understand, but it is the same thing, and you can look it up to see the actual formulas, but you'll notice a lot of similarities. Then there's the extended Kalman filter, and this is this allows us to apply the Kalman filter to nonlinear models. So nonlinear models for state dynamics and for observation processes. So this is achieved by linearizing the models around the current estimate and using their derivative. So it's not exactly the derivative, it's the Jacobian, which is basically the derivative with respect to all other other state variables, but it's still basically it's a derivative. It just changes it slightly, and you essentially have a very similar form, but the way you calculate the covariance changes to use the Jacobian, and then here in the prediction step, we actually, instead of using matrices, we use just the function that, like the nonlinear function that we would use normally. So like you can take sine of, say, your angle or something like that. The accepted Kalman filter is it's probably the most different of these 3D filters. And what it does is it essentially propagates special points through the nonlinear functions and then reconstructs this mean and covariance. So instead of using like this formula essentially to calculate this covariance, it just runs it through the function and then essentially reconstructs it from that. It's a little less, so it's less efficient than an extended Kalman filter because you have to do it like multiple times because you have to do it for every point. But it typically does better for very nonlinear functions. And it also allows you to perform Kalman filters without calculating the derivative, which sometimes it's really hard to calculate the derivative. And that's another advantage of the extended Kalman filter. So yeah, that basically concludes Kalman filters. But I said what we use, I would tell you what we use in RoboNav, at least. We use the extended Kalman filter extensively. It's our main localization ball filter, I guess. I've also worked on a project for an internship, and they were using an unscented Kalman filter to get their position. But this is like the most extended Kalman filter and the unscented Kalman filter are the most common ways of performing localization, I would say. There are other ways. So Kalman filter is not the only localization algorithm. There's like a lot of like factor graph based localization techniques, and those come with their own advantages. Mainly that they allow for basically like sparse representations of the state, which we're not going to talk about, but they can be more efficient essentially. But yeah, extended Kalman filters work very well and are used a lot in practice. So any questions about the Kalman filter? There's a lot of stuff in that, but hopefully found it helpful. So a couple of seconds in case there are questions. Okay. Cool. Well, if there aren't any questions, I'll move on to the second topic today, and that's particle filters. Will we implement one for the exercise? I believe, yeah, you will. You'll implement one in 1D, so it'll be a much simple. Well, it'll be a simple case, but you will have to, I believe, tune the parameters and stuff like that. So, yeah, Kyle, if you want to.
Yeah, the exercises, we were a little bit late on finishing those up, so they should be out like later today, maybe, or early tomorrow. I apologize for that, but we won't be able to get you the links quite at the end of this meeting. But yes, you will be implementing both a Kalman filter and a particle filter.
Yeah. So if you found the Kalman filter to be very heavy on math, you might like a particle filter because it's a lot less heavy on math. Basically, it uses a simple algorithm to estimate the pose of the robot. Of course, there's drawbacks to it, but the algorithm is basically you initialize n particles, either evenly scattered in your map or based on prior knowledge of where your robot starts. You then, for every time step, you update the position of each particle based on that just known state transition model or on the odometry readings that you're getting from the robot. We then calculate the probability that given the robot is located at that particle, you would get the sensor readings you got. So similar to the sensor model, to the thing we did in the Kalman filter, but we don't have to calculate a Kalman gain and all of that. And then we set this probability as the weight of the particle. And then the last step is we're just going to sample the particles based on the weight of the particles. So I'll go through each step in more detail, but this is just the general algorithm. This is actually a particle filter working in progress. As you saw in the beginning, there were a bunch of particles everywhere. So it was just evenly distributed. And as the robot moves, you'll see these clusters of particles begin to form. And these are your best guesses of where the robot is. The one with the most particles essentially is your best guess. And as you can see, for a while, it doesn't know where it is. It's either here or here. But once it enters this room, these two rooms are actually different. So when it was in the hallway, both like entering this room and entering this room is exactly identical in terms of sensor readings. And so you had those two estimates just moving together. But as soon as I entered this room, there was this obstacle here that isn't in here. And so because of that, this cluster died out and you got your filter converged on your actual position. So yeah, this is just like a particle filter at work. One thing, this is basically shows that the algorithm is actually multimodal. So one of the disadvantages of Kalman filters is that it was unimodal. It could only track one position. Here we were tracking two positions that were almost equally likely. And then only once we got information that distinguishes those two positions could we say, we are definitely here and not here. Yeah. So step one was to initialize all the particles randomly. So what do I mean by particles? It's basically just a vector that represents your entire state. So everything you care about. In this case, the particle is representing x, y, and theta. So this would be for a 2D robot where we care about which way it's facing and its position, and nothing else. We can also capture velocity in this. We could capture acceleration or whatever we want in this particle, but oftentimes particle filters use, this is like what they'll look like. It'll just be like position and an angle. And I'll explain why, but in 3D, it gets more and more expensive to do a particle filter the higher your dimension. So so we initialize n particles, and n is a parameter you choose. So typically this will be like thousands. So it might be like 500, it might be like 1,000, maybe 10,000. So it's a very high number of particles, and you need that to estimate the state well. The larger your n is, the better your estimate will be, but the more computationally expensive it will be as well, obviously, because you have to update every particle in every step. So the motion update. So we use the odometry or knowledge about how the state will change over time to update the position of each particle. So we'll basically loop through all the particles, and for each one, there'll be one odometry measurement, right? So we know that we moved, say, square root of 2, or at least that's what we think we moved, or how far we moved. And then we can use coordinate transforms or any other way of converting that from the robot frame to the global frame. And basically, we can calculate that that new position is at 3, 3 and angle of 45 degrees if we start at 2, 2, 45. All we're doing is we're applying essentially a function directly to this state vector. There's no matrix. Well, it can be a matrix, but it doesn't have to be. And that's one of the advantages of the particle filter, is that it's very flexible. And also additionally, we will generate some noise based on our noise model our process noise model. And we will add it to each particle to simulate that process noise. So if you remember Q in the Kalman filter, this is essentially doing the same thing. It's just the Kalman filter Q had to be a Gaussian function, so it had to be a normal distribution. With a particle filter, it doesn't have to be a normal distribution. It can be like that sensor model, or not sensor model. It can be like any model you want. So you could have a uniform distribution or a peak, or I don't know, whatever you want. Yeah, and so what we get from that is that the particle will essentially move to this new position and new angle. And the reason you want to add this noise is because as your filter converges, you will have a bunch of particles very close to each other, or even at the same position. And you want those particles to represent a bunch of the possible states that the robot's actually in. Because the better this, after this motion update, like the closer your particle is to the actual position, the better the filter will perform. For each particle, we then compare the expected sensor output from the sensor model with the actual sensor output. So for example, say we have a sensor that gives us our position, and it gives us a reading with a normal distribution and with a variance of 1 centered around our actual position. So this is like, again, we're using a Gaussian here, but you could use any model you want. If the sensor says that we are at 2,3 and we are like the particle itself is at 2,2, then the error is just 1, right? Because it's just 1 in the y direction. And the weight we would give the particle is 0.242. And this is just looking at that our sensor model. We go to 1 here, and we're looking at the value of the Gaussian function, and it's literally 0.242. If the error was 0, we would use 0.4 because that's where the peak is. So that's all you do. It's mathematically very simple, but you do this for every particle. So you're going to be doing this like 1,000 times. Yeah, then we compare the. Oh, sorry. What is it? Yeah. This step, yeah, it can be repeated for each sensor. If you have multiple sensors, what you do is you just calculate that weight that we did previously, and we just multiply it together, like all together for all the sensors. If a sensor doesn't give you a particular parameter, you just multiply by 1 essentially. So it doesn't affect it. Well, for that particular value. So yeah, after we compute the sensor update, we normalize the weights by dividing the weight of each particle by the sum of the weight of all the particles. And that was weight of the particle. So the weight of the particle is essentially just the I'll have a, yeah, it's literally like you just have like a value associated with each particle, and it actually ends up representing the probability that you're going to resample it later. But in reality, I guess the weight, what it means is the larger the weight, the more aligned that particle is with the sensor readings. So if you have a sensor reading that makes sense with your particle, that particle will have a higher weight. If your sensor reading doesn't make sense with your particle, so like say we are at 2,2 and facing 45 degrees, and it says we are at like 50, 100 and facing down, then the weight of that particle would be really, really small because it doesn't make sense with the sensor readings we are getting. So yeah, but it's just a value associated with that specific particle. Kyle?
In general, it's also usually considered like the likelihood, like the conditional likelihood of receiving that sensor measurement given that you're in that state, right?
Yeah.
Like that's often a way of looking at it.
Yeah. Yeah, like I said, it can be looked at as a probability almost. You'll see it gets converted to a probability, and actually here it gets converted to probability that we'll choose the particle. So yeah, we normalize the weights by dividing the weight of each particle by the sum of the weights of all the particles. So this is done after we do all the sensor updates. We then just go through all the weights and divide them by the total weights of all the particles. And this So yeah, this results in getting essentially a probability, I guess, of how good. Well, it's probability for resampling later. So yeah, so after we did that, you'll see some particles will essentially be really big, and or like have large weights, and that is and that's because the particles the particle is closer to so close, so closer particles to sensor equal more weight. So yeah, basically the particles are more aligned with the what the sensor model will give, and therefore they have higher weights. And then you would the other particles essentially are less aligned, so they get smaller weights, and you can present them as like bigger or smaller circles or whatever you want. And the last step is replacing. Essentially, we resample all the particles with substitution, and we use the weight of the particle as the probability of choosing that particle during the resampling process. So, so this means that the particles with greater weight are more likely to spawn multiple particles, while particles with lower weight are likely to disappear. And that's what you see here. So, for example, this one particle essentially now has 4 particles representing that state. And this particle here, that there was like there was only 1 particle to begin with, and then it also became like small due to the weight. It now just disappeared, or these essentially become 1 particle. And usually you keep n constant, so so you're just going to resample n points with these probabilities. So, and we'll loop through steps 2 and 4 until the program is terminated. And that's basically it. That's the particle filter. And to recover our position, we just look at the area with the most particles. Like how to do that in terms of like how do we do that actually in code? It's usually done by having like a set radius and then looking at essentially the mean of the particles in that radius. You don't want to do the mean of all the particles, or you'll get like really bad estimates when you have the 2 large groups of particles. But yeah, that's I mean, if you're going to implement a particle filter, you can look up a more detailed like code well, like pseudocode, but yeah.
Yeah, it just depends on the application. Like in
Yeah.
research that I do, you just take the weighted average, and that's usually fine because we essentially can pretty well assume that we only have 1 group of particles. If you start getting to where you can have multiple groups at the same time, it gets a little bit more complicated.
Oh, yeah. And I think I said terminated. Here I mean like we no longer need a state estimate by terminated. There's also sometimes you will terminate a particle filter early if it doesn't converge correctly. So like, oh, sorry, let me choose the conditions. Yeah, the program terminating is like literally just like the actual, your robot code is terminating most likely. But there are sometimes when you would want to reset a particle filter. So one of the issues with particle filters is that if we have no particles in a state, it can't like model that state essentially. So if, say at the beginning, there are no particles in the correct state, the filter will never converge, unless you do other things, which like I think I'll talk about later. I think I did, but yeah, if not, I'll mention them later. So yeah. So this is just a quick example with like a very simple case, even simpler than our localization, like a 1D localization, I guess. And essentially, we have 4 states, just 4 states, and we start off by just distributing the particles evenly among the 4 states. And we give all of them an equal weight. I didn't mention this, but essentially, if you don't, whenever you're resampling, you're always going to give all the particles an equal weight. So then we have some transition model. In this case, there's an 80% chance that it'll go in the right direction, and then 20% chance that it'll go perpendicular to the correct direction. I guess so. Say we took an action right, so we said move right, but Sometimes you'll see that even though we told it to move right, some of them moved up or down. And essentially we get a new distribution of particles, and they're all still equal weights though. So this is that first step, or second step, I guess, in the slides. Third step is we receive a sensor reading that says that there's a wall to the north, and based on our sensor model, it's essentially we want to find out the probability that we are that we get this sensor reading given we are in this state. So so the probability that we would read a wall to the north if we are in state 1 is going to be equal to 0.073, and that's just calculated based off of our sensor model. This could be anything though, like it could be a Gaussian. There's a lot of that's the nice thing about particle filters. Your sensor model can be anything, but it depends on the application. But what you'll see is all of the particles now have different weights, or well, a lot of them do. So the last step is we resample according to the weights. So as I said, we normalize. Don't worry about this too much, but but basically it's we are just this just explains like how we would resample. But we resample the particles based on the weights, and the particles with larger weights end up turning into more particles, and in the end you get basically the same situation as you had earlier, except now you have more particles in the positions that are more likely to be correct. And yeah, that's yeah, that's basically it. So one of the things I wanted to mention is like, so say you are now in state 2 is actually the correct position. There is a chance that you would never find out because there are no particles to model it. And so one of the things you can do is you can sprinkle in random particles as well along your map over time. And this allows you to potentially recover if your model did not converge correctly. Another thing is you can detect if your model didn't converge correctly, or try to at least detect it. And then if you see that it hasn't converged, you can restart the model and just do it over again and hope it converges a second time. So particle filters aren't exactly deterministic. So they're not deterministic usually. So there's a lot of chance that goes on. But if you have enough particles, you have a very good chance of converging, and it does work as a localization technique. So now I don't know if this will, hopefully this will work. So this is robot. So I found this online. This is a RoboCup, but I believe this is this is a very different version of RoboCup than we do. But basically they have a robot and it's hitting a ball around, and you can see how the particle filter is essentially tracking both the ball and the robot using a bunch of particles, and you can see how it can tell where the robot and the ball are just by applying the particle filter. Also notice that when the blue ball hits the wall, it scatters everywhere, and that's because you can have different well, during that transition model, you can apply a lot of noise to one model and not the other, and essentially the position of the robot can't change logically. It can't just go everywhere. But a ball, it'll bounce around, and it's hard to predict the exact position. So it has much more uncertainty, and that's modeled by the fact that the particles end up going in much larger spread. They have a much larger spread after hitting the wall. Yeah. So the advantages advantages over Kalman filter, you can tune the accuracy of a particle filter versus the computation time by setting n. So the higher you have your n, the better your filter will be. But obviously, it's expensive to increase n. It's also multimodal, so it can track multiple position estimates at once. Another big one is that you don't need an initial estimate. Well, it's good to have initial estimate, but if you're not really certain where you are, you can just spread out particles everywhere at the start, and the model will still converge. With a Kalman filter, I mean, you can kind of do that by setting the covariance really large at the start. But if your sensor readings are really noisy, it could have trouble converging. So yeah, there's also it also does not assume linear models or normal distributions. So you can use the actual models for how your robot moves and for how the sensor readings act, like what the sensor readings actually look like. And that's another really big advantage for particle filters. Now there are some disadvantages especially if you don't have enough particles, or if you don't have a lot of sensor inputs. You can have very jumpy behavior. So I think in the first video, or like GIF, I guess I showed, you saw that it jumps position really like a lot at the start, especially before it converged. And for a robot, this can be pretty bad. It depends kind of on your application, but like jumping to a different position and then jumping quickly back can be really disastrous for some robots. So that's one thing. It's typically more computationally expensive. I would say I think it's always almost always more computationally expensive. And another really big thing is that as you increase the number of dimensions of our state vectors, so like we had 3 essentially dimensions like x, y, and theta. As you increase that, you need a lot more particles to represent all the states, like possible states. And that's just because every time you increase a dimension, like if you think about if you have a line and then you have a plane, you would need double the amount of particles to keep the density, or not double, square the number of particles to keep the density the same. And so it just gets worse and worse as you increase dimensions. So if you have to keep track of all the positions as well as all the velocities, so that's like for a 3-dimensional system, that's 6. Plus you need to keep track of angles, that's 9. You're essentially working with a 9-dimensional vector, which means you're going to need a lot of particles to simulate that. So this is a kind of an overview of what to use when, but all of these are like kind of with a grain of salt, like because it really depends on your application. So if you have no good initial guess at all, you might lean more towards a particle filter. If you do, then you have to like examine how linear your models are. If they're completely linear, you should probably use one of these two. So information filter or Kalman filters. If it's close enough, you can use an extended Kalman filter. And if it's not at all, then you can use an uncentered Kalman filter. But again, like these two, for example, like it's not that, like sometimes you don't care about computational cost too much, at least, and you care more about getting a great estimate. And so then you might use an uncentered Kalman filter instead of an extended Kalman filter. Also, information filter packages are, I think, more rare than Kalman filter packages. So like it just might be easier to implement the Kalman filter. So yeah, so that's it for the presentation. If you have any questions, yeah, put them in the chat, I guess. If not, then yeah, that's it. We can.
All right, so we're going to be heading off to breakouts in a second. First, I have a regularly scheduled pacing form. We've been sending these out every week, but we send them out in the emails usually, which is questionably useful. So I'm sending it here. The only new addition there is we want some feedback on the free work period that we had last Thursday. So if you could give us that, that'd be great. Also, if you have not yet done it, stick around for a minute. Otherwise, please go to your breakout room. I believe we're doing RoboNav and RoboRacing combined today, right, Daniel?
It's fine. I can do my meeting.
Okay. In that case, everyone head out to regular breakout rooms, and we'll finish this up. Thank you, Andrew, for an excellent presentation.